So today I'm going to tell you about this harmonic RFID, okay, with probably I'll emphasize a little bit more on the real-time locating, okay. But in order to talk about the why this is different in real-time locating, I have to go through a little bit on the harmonic RFID design, okay. But I'll try to save time on that so we can have a more discussions on this real-time locating indoors, okay. That's the one of the very difficult technology for RFID today. Okay, so that let's spend more time on that. And please stop me for any questions. I don't get offended, okay, at all. Okay, I cannot tell you how many I have. Many of my recent work or inventions is out of very harsh questions to me in the presentations. Okay, those actually push me to think for the next step. Okay, so please interrupt me anyway that I can try my best to explain to you what my thoughts are. Okay, so I'll tell you about the motivations of a different way of doing a passive RFID, called the harmonic ways. Okay, this is not really new. Okay, been going on for quite a while back from the radar days. Okay, but we developed a more theory implementation experiment for this concept. Okay, I'll tell you about the harmonic generation of a specific way called the nonlinear transmission line. Okay, it's not just a simple nonlinear element. But this nonlinear transmission line have two important properties I need, okay, for the real-time locating. Okay, so you will see that how I'm going to map that into the match for giving me good locating capabilities. Okay, so I'll go through a little bit on the reading range characterizations. If time, I don't think we'll have good enough time today, so I probably will skip all the data modulations, which is not too much different from the present RFID. Okay, just that if you haven't working with the present RFID, either in BPSK or something, that you can do similar things there. So there's nothing really new here. I probably will skip a lot of this, and I'll spend enough time to talking about ranging and locating, which is one of the main problematic area for today's RFID. Okay, you can read the ID, but you cannot locate it. Okay, you cannot get the good ranging and locating things. Then I'll conclude the talk. Okay. So there are two categories. I can skip this. This is the holy land for this, where you have NFC and the backscatter. So I'm only talking about restricting the talk to only backscatter RFID, and it's passive. Okay. I know there's a lot of active work RFID here, but for the purpose of the talk today, okay, I'm only going to talk about passive backscatter microwave RFID. Okay. That's the only thing I'll be talking about. Different applications, different modes can work better. Okay, that's but I'm restricting to that. Okay, I'll skip all that. The RFID, if you can do things, will be great, right? Because the tag is no passive, there's no battery. You can use in many things. Maintenance, deployment become much easier. You can have all these funny applications. Item level RFID. You can do all the body area network things. Okay, so. Promising, okay? So there are two things that's contained in the backscatter RFID, okay? One is the digital code, okay? You modulate the backscatter wave to send about this half a K to 4K bits, okay? Yeah, and these are the you can use this as a digital mode. Okay, the security is a big topic for that. In the analog way, okay? In analog information in the carrier, there are also information, okay? You can tag a sensor, okay, usually to it, say you change the way the antenna or the how reflections is done. You can usually get a 4 to 9 bits of sensor outputs. Okay, that means I can get about 200 levels accuracy, okay, in that. And also more importantly, that they are the location, because of the backscattering, just like radar. Okay, the location information is embedded in the analog information. Okay, that so what
do you mean by sensor outputs?
Sensor outputs, say you have a sensor capacitance, okay, and I want to read because of the things you're sensing, pressure or chemical concentration affecting the capacitance or the work function, right? Okay. And that I want to read all the levels, not a digital code. Right. Digital code, you have different ways to read it. Yeah. You have all
the about like an analog sensor.
Analog, right? So the sensor is made most of the time is not digital, right? You have to digitize it, right? So the things you get back is a level of pressure or level of something, right? So you can read it directly. Okay, it's very difficult to have an A to D converters right at the tag.
So you just do it, get it back.
Get it back and then do the analysis indeed. Okay, so conventional backscatter is just the shower the tag with the fundamental wave and the backscatter with a modulated information. Okay, so for sure there are main interference path from any objects in the room. Okay, anything, especially metal or ground. Okay, that's reflecting a lot of the things, and many times this is much closer than the tag. Right, so that you can imagine that these reflections it's very strong. Many times you can even drive if the frequency is high enough and your radiating power is enough, your room can be in resonance. That means all phase information lost. Okay, another very important interference is self-interference. Okay, self-interference is just how your readers, transmitter and reader, right? They actually have leaking through here, and this is actually, if you look at it, although this is more predictable, so you have ways to deal with it, but this is actually in the interference, this is the biggest interference. Okay, you're leaking to yourself, right? You try to generate the F0, but unfortunately, okay, your readers also receive, right? Your reader antenna, you can use polarization, whatever, to isolate it, but this is usually only minus 30 dB. Okay, that's just for your own interference. So we propose these, not propose. Okay, another way of doing it is something called harmonic RFID. Okay, you shower the tag with the F0. Okay, you collect power or whatever in that, but the reflected wave, there's a nonlinear element in the tag that reflected the second or third harmonics. Okay, so because third harmonic is far away from the fundamental. Okay, so the filtering becomes much easier. Subharmonic, okay, is much harder to filter, right? Because it's too close. Okay, you need very, very expensive and high order filters. But to filter the signal, right, in the second or third harmonics is very simple, okay, because it's far away. Okay, so most of the self interference and all the reflections, okay, is on the first order gone, right? Because unless you have nonlinear materials, okay, in these frequencies, then it's not reflecting in the second harmonics. There are things like that called ferroelectric, but we don't have a lot of ferroelectrics in the room usually. So this is something that's dramatically reduced for the interference. Okay, so also the isolation is much easier because again the readers only care about the second harmonic. Okay, so you can do much better self isolations for that interference. Okay, so in a room, there's no strong harmonics even for indoors, right? Hardly be in resonance, okay? And because the reflections is in passive mode, it's not under FCC, and the second harmonic and third harmonic being reflected, the backscatter signal is not under FCC regulation. Okay, so you can just choose the fundamental that fit the FCC. The backscatter actually doesn't matter. Okay, there's no regulations. Uplink still have multipath, right? So the multipath become, I reflected this and only the uplink reflection, I have multipath. Okay, I didn't eliminate all the multipath, but many of the multipaths has been eliminated. Not all. Okay, there's still multipaths exist. Okay, it's probably better showing here, right? So if you look at the multipath for F0, if you have a tag intended, and this is many of these reflectors, you can see that now the only multipath is these two F0, right? Reflecting here to the receiver. Okay, none of the other F0 have a lot more multipath. Okay, just that the harmonics now have much simpler multipath analysis. Okay? So that's one of. But how good? Okay, how much I have reduced for that? We can go for the equations, which I'm not going to in the details. Okay, so these that you can figure out all these multipaths from things that causing the two errors. One is the errors to the signal to interference ratio, and the other is the phase noise. Okay, that you can play with your wave equations and figure these out. But is actually dramatically reduced. Okay, so this is a Monte Carlo simulation trying to put many of the reflectors in random positions. If you see for the regular conventional tags, the mean of the power error is not that bad. Okay, so there's still why that you can still use the F0 for a good purpose because the mean is not bad. Okay, even the standard variation is not bad. This is the box part of things, but you can see that is the worst case that's bad. Okay, there's some reflectors and some arrangements, right, of the reflectors can give you large phase amplitude or power errors. In phase, it's even more clear. Okay, on average, it's not bad. Okay, reflectors that in fundamental multipath that on average is look like only 15 degrees phase errors caused by many of the reflectors. But the worst case can be 180 degrees. That means the phase is no use. Okay, so if you look at the nonlinear harmonic reflections, okay, these are the case for both the much more reduced, even in the worst case, okay, much smaller phase error as well. Okay, much smaller. That's how much using Monte Carlo simulation try to tell you that how much you improve. Okay, how much it doesn't eliminate the entire problem, but dramatically improve the signal to interference ratio and the phase noise of the reflected wave. Okay. So we try to verify this by experiment. Yeah, real room, real metal cabinets everywhere. So try to put reflectors, aluminum foil balls in many places. Okay. So you can see that is real in that sense. Okay. So in the nonlinear tags, you get a much better signal to noise ratio. Okay, in different ways. Right. These are the conventional tags. In phase error, actually phase error I cannot even measure for the conventional tag, it's too large. Okay, cannot capture that. And my harmonic reflections is always bounded by 4 or 5 degrees. Okay, with putting a lot of these balls, tennis ball or basketball wrapping aluminum foil. Okay, so that's the actually match with my Monte Carlo simulation pretty well, so I can believe that the Monte Carlo simulations data is good. Okay, and so because of this, right, many people have been trying to work on the harmonic way. Okay, so I'm not the only guy. There's one person, one work back in the 06. Okay, that's the generated harmonics from active waves. Okay, but there's one way to do it. It takes quite significant power. They are using nonlinear elements, just like a diode, to generate harmonics. Okay, so apparently the diode then is, as this is a nonlinear capacitance, you need matching network. Okay, you need put matching network for that nonlinear elements, and this is usually pretty large inductors tank. Okay, both for the fundamental frequency and for the harmonic frequency. And these are, and all passive matching network, unfortunately, is narrowband. Okay, so that so you have to separate the two matching network for that, and you use a very significant inductors to bring the impedance back to real. Okay, so that you can match to the antenna. Okay, or else you have nonlinear elements only capacitors, right? So these you have to use matching network for that.
These are discrete wound inductors, right? These are discrete wound inductors. You don't
for these experiments. This is not my paper, so but they do use discrete inductors. You can 8.2 nanohenry is doable by integrated. Okay, doable. Okay, but in significant area. Okay. Dipole. Okay, this another design out of Florida. Okay, so there's another way of doing how it comes in this antenna, go out in that antenna, having their own individual matching networks. So let me tell you why I take a different approach. Okay, I use something called nonlinear transmission line. I work on nonlinear transmission line not for in the beginning, not for RFID. Okay, I have my own purposes of edge sharpening or oscillation, generating UWEV pulses and things. All of a sudden, because of a wrong tape out, the student do the layout wrongly. And we measure, for sure there's no sharpening, none of the things I want, but the harmonic is so big. Okay, harmonic generally is so big. So I look at what is so good about it. Okay, so that's actually the accident. That's the start from many good properties. Okay, out of that error. Okay, let me tell you what is nonlinear transmission line. Okay, it's very similar to the diode, but now it's a transmission line. Is that you put these discrete nonlinear capacitors as part of the transmission line. Okay, it's like your big L and 1C, right, as a discrete element for that narrow band thing. I distribute it to a traveling wave. Okay, distributed to a traveling wave. And this is something that has been studied for 50 years, okay, 50, 60 years, called the KDV equation, these soliton circuits and all the things behind it, okay? Okay, but this is something that rather similar to that L matched into a varactor, okay? But it's in propagation mode, okay? So what my student did wrong is when one implementation is flipped. So it's a varactor, but it's a varactor with alternating CV things. So originally, right, you propagate a wave on this, a soliton will form because the higher voltage will propagate slower than the lower voltage, right? So they form into a soliton, okay? But when one of the tape out is wrong, they flipped, okay? So only the nonlinearity matters, but we measured a very gigantic harmonic conversion, okay? So look at this nonlinear transmission line. There's a few things that's not in the original, just one L and C. Okay, the first thing you notice that if I put into a lattice gives you a Bragg frequency. Bragg frequency means over some frequency, there's only impedances mode over that frequency. Okay, there's no active propagations above some frequency. Okay, these can be used very well in nonlinear conversions because a lot of the power is lost to spilling. Okay, when you put in nonlinear elements, you will spill power to all the harmonics. Okay, you put a Bragg frequency, then I put between the second and third harmonics. There's no conversion to third harmonics. Okay, the only possibility is going to second harmonics. For sure, the phase matching doesn't spill to third, doesn't give you the high efficiency in second. Okay, you still need to work out the math to do the. But this one gives you a good limitations. Okay, there's no spilling. Okay. The second is a broadband impedance. Okay, if you plot the nonlinear transmission line, the impedance I'll show you immediately. It's a broadband oscillating conditions. Okay, I can find a relative broadband where I do not need any matching network. Okay, you can see the antenna is a transmission line, right? Okay, think about it. It's the simplest transmission line, simplest antenna is bend your transmission line to 90 degrees. Right? So that the transmission line can work with a broadband matching. Okay? Broadband is matching is a very important thing to harmonic and especially for the locating. Okay? I'll show that why this is important. Okay? So this is a nonlinear transmission line generate, and so you can once you conversion we figure out how that the nonlinearity the varactor you are given. What is the inductors you can do? Okay, then you can construct the correct nonlinear transmission line for the harmonic conversion purposes in the right impedance. Okay, so there are big equations. I apologize. Okay, that you have to phase match and things conditions, but we figured it out. Okay, it's possible. Okay, how to generate this largest second harmonic or third harmonic conversion with the correct Bragg frequency with the correct impedance that achieve that phase match conditions. We figured it out. Okay, we figured it out. Too long to bore you for that. But and you see that the without counting the insertion loss for the matching network, I'm already much better, okay, than the single discrete implementations, and these strictly coming from the good phase matching conditions I can do in NLTL and no spectral spilling. Okay. Okay, so this one actually can be a lot worse if you add the insertion loss of the matching network. Okay, depending on how good is your inductors that you can get. Okay, but even without that, just for the conversion rate. Okay, I'm already 7 to 10 dBm better. Okay, for the conversions than the discrete. Okay, so these are all the calculations. How to guarantee the dispersion is in check and phase condition is checked. There are sweet spots you can design that give you the maximum harmonic conversion and the correct impedance match. Okay, so that's prototype. Okay, we have prototype in both the PCB depending on the frequency range. Okay, as low as the 900 megahertz on PCB, or as high as like 10 to 25 gigahertz in the integrated circuits. Okay, if you use something like this, okay, then a discrete. This is a semi-distributive NLTL. Discrete NLTL. If you use discrete elements to implement your transmission line, then you can get right a 10 gigahertz nonlinear transmission line as a Bragg frequency. Okay, 0.4 to 1 millimeter. Okay, very puny. Okay, very, it can give you very nice harmonic conversion already in that frequency. Okay, and simulations and measurements. Okay, match really well. Maxwell equation. One great thing to work with Maxwell equations, that the harmonic conversions can be very well predicted. Again, we get about from measurements, right? The second harmonic conversion is minus 10 dBm conversions over a pretty broad band. Okay, pretty broad band. And the third harmonic is a little bit worse, about minus 14. Okay, minus 14 dBm. Okay. And transmission line, then you can see that there's one way to do transmission line, F0 coming out, propagate through this nonlinear media, and 2F0 getting out. Or you can put a load, right, a reflected wave, so that is see the traveling for two times. Okay, you can do that as well. So the design is a little bit different. Okay, to guarantee the phase matching conditions, and also put the penalties on the antenna need to be dual band. Okay, so that's. But it's a simpler design for reflective. Okay, because it's not two antennas. Okay, it's not. But you can use a reflections, right? Playing the burdens on two antennas. Okay, on one antenna. Okay, and we figure out most of the design equations for comparing the different things. Okay, you can terminate it with a load, like sensor capacitance. Okay, reading the sensor capacitance from the in the analog mode. Okay, so to read these capacitance as a load in reflective. Okay, and you can also do as an open circuit or short circuit. It has a different way to optimize your non-harmonic generations. Okay, we all figure out. And the impedance looking like this. Okay, so you can see that because of the construction of the wave equations, the impedance is an oscillation. Okay, so they are relatively good matching within a bandwidth of 1 to 5%. Okay, that doesn't really exist in the discrete elements. Okay, so but in the transmission line, is having things of the windows that you can take for impedance matching. Okay, impedance matching, relatively broadband within its own frequencies, and these can be calculated, designed, and then implement your nonlinear transmission line. So we also tape out these things in a relatively high frequency, and these become even smaller. Okay, so these become 1 millimeter by 0.3 millimeter nonlinear transmission lines. We characterize how just the nonlinear conversions. Okay, these the oscillatory signals coming from the oscillatory impedance match. Right, when things does not match with your the harmonic generation does not match the impedance, right? Then it's the S11 will have a peak, right? So something just directly to the impedance. Okay, harmonic generations in reflective design. Okay, also that you about minus 10 dB. Okay, minus 10 dB loss for the harmonic generations. Much better than the discrete already. Okay, so you can then characterize the reading. Okay, let's do this quickly. Okay, range characterizations. So, okay. So the radar equations give you 1/d force power, right? So this is the radar equations for the conventional RFID. Okay. Harmonic is doing a little bit worse than that, so that's a trade-off. Okay. So using why harmonic radar is not the usual radar you see. It's probably out of this parallel, right? In conventional radar, with all the interference, but the loss is 1/d4. Okay. Harmonic, it's 1/d6. One slide, 1/6, right? Because the 1/d square, right, the amplitude at the receiver side, right, that determines how much harmonic you can generate. So this additional, the downlink d square is squared. Okay, so it becomes d6. Okay, you can see the experiments, right? It's right on the 1/d6 line. Okay, yes.
That's free space.
That's free space.
So indoors, you get another at least 1 or 2 in the exponent, right? Because indoors is usually 1/r cubed for just the overall amplitude.
Yes and no. Okay, so
Okay.
so the indeed indoor measurements will be a little bit more complicated. This actually measure in the room like this. Okay, with camera. Okay, so that the conversion, right, all the reflected wave, right, that's fundamental frequency. That's probably in the nonlinear transmission will generate the harmonic power. Okay, yes, you're right. Okay, so this needs to be experimentally verified, but there's a fundamental disadvantage. Okay, is that you take additional loss at the harmonic generation. There's a fundamental advantage that self-interference and multipass become much simpler. Okay, so this is a trade-off. Okay, this is not a panacea for all situations. Okay, but you take the hit at the harmonic conversions, but you reduce the load on the self-interference and multipass. Okay, so this is for digital ID. Actually, we go through all the formulas, and then the advantage you get is not too big. Okay, there's advantage, there's disadvantage. So you can do RFID in this way. Okay, but just that because it's a fundamental advantage and a fundamental disadvantage. Okay, so it's you don't bring a lot to the whole things. For our implementations, you compare with slightly better in range. Okay, slightly better, but not a whole lot better. Okay, because there's but do think about this. 1/d6 is much more localized. Okay, even in the same range. Okay, it's much more. That means the far away the interference is even less important. Okay, it's a much localized. Yes.
No, just making comment for myself.
Okay, no problem. So, okay, and at the 0.1 watts, right? You can get this 1 meters using just a monopole antenna. Okay, that is not bad. Okay, you can raise the pulse power a little bit more using a better antenna. You can extend to 8 to 10 meters range. Okay. So antenna, I'm not going through the antenna. So the antenna will have this funny radiation pattern. So in order to do reflective, remember now one antenna need to do 2 frequencies, right? So we do the G-shaped antenna. This is a small monopole, or the D-dot antenna can look like. Okay, they have a specific patterns where you measure how much harmonic power you can have. Reflective, it's about. You also get about a range 0.1 watts. Okay, reflective is a little bit worse in the range. Okay, you get about 40 centimeters. Okay, in the 0.1 watts shining.
Do you have polarization issues here? Do you get polarization scattering?
Yeah.
Randomization? So
Yes,
you
you
lose
can.
from that too?
Yes. Yeah.
Is it different for the harmonics?
Depending on the antenna, right?
Okay.
So yes, but the G-shaped antenna is in the same polarization for the fundamental and the second harmonic.
Oh, okay.
Okay, so in putting everything in comparisons, we are currently the smallest and the highest range of harmonic harmonic RFID. Okay, yeah, with our implementations using the nonlinear transmission line with discrete diode. Okay, it is better. Okay, better than all the other implementations. Okay? So this work has been finished publishing this about 2 years ago. Okay, so, but since it have a fundamental advantage and fundamental disadvantage, okay, doesn't generate a lot of big excitement. Okay.
So when you say the reading range, for example, for this, you call it reflective NLTL. This is the one where you can attach the sensor tag and read it.
Yeah. Sensor. I'll do the sensor tag information just now.
So that means
that's tied to locating actually. Yeah.
Yeah. So on half a meter, 0.45 meter, that
Okay.
means that you can get the accurate reading.
Yeah. Yes. So this one people do different receiver sensitivity. Okay. So this one is usually at minus 85 dB sensitivity for the reported data. Okay. So if you do active, then many people would like to have a cheaper receiver that is minus 70 sensitivity. Then the number needs to be continuously reduced. Okay. Or you have to boost up to the transmitter power. But all in fair comparison, okay, fair standard comparisons were still the best work out there for harmonic RFID. As I mentioned, this is not a dramatic improvement for the conventional. Okay. Okay, data modulations. For time's sake, I'll jump over the entire data modulations, except this one. Okay, that seems to be of some interest. Okay. So this is also where the locating coming from. So we measure, okay, we change the sense capacitance as the ending capacitance, and we try to measure the phase difference, okay, the phase difference of that caused by the change in the sensor capacitance, okay, and then we figure out this line, very stable line actually, okay, very stable lines and things. So we get in the different designs about 0.25 degree per femtofarad change in the sensing capacitance, or in another design, okay, 0.16 degrees of per femtofarad change. Okay, so this one, right, for the range of the change of the capacitance, that give you, right, if you have this, right, give you about 9 bits of the precision you can read of the sensing capacitance. Okay, but then when I measure this, I ask the students, say that if somebody open the door, or if you walk around, what this data being affected, he says he doesn't know. Okay, I say, how about you measure it? That this is collect the data for a long time, right? You move around, you're doing funny things, you wave your hand and things change. It doesn't change. Okay. I was possible to say, I'm asking the question, say, if the phase is accurate and stable, then all your locating information is in the phase. Can you give me this phase to locate it? Okay, so that trigger, right? Why seeing that this is stable, walking around and under different environment is stable? I asking if you can collect the stable phase, the ranging information is embedded in the phase. Okay? So that's the start how we look at the locating techniques. Okay, but there are many locating ways. Okay, I see a lot of work in your previous review. Okay, so okay, then let's don't look at this. Okay, only looking at the RFID passive mode. Okay, you can get from the signal strength. You can get from the phase difference. Okay, signal strength is a lot of problems. Okay, the phase you have to deal with the fundamental issues of bandwidth, and they call the wavelength ambiguity. Okay, there are two things in mind. Because of the reflected wave, right? The ranging, the range is coded in there, right, by the phase shift. But you have two problems, right? The phase shift represented by a bandwidth, and the phase shift, right, that you don't know every quarter wavelength. That's the ambiguity point. Okay, so that's but there are two fundamental things. Although phase gives you much more reliable and accurate locating informations, but you have to resolve two things. Okay, the bandwidth issues and they call it wavelength ambiguity. Focus on that. Okay, and this is well known. Okay, even in all radar mode, right? So it's actually a RFID, right? So it's a radio detection and ranging, right? That's radar, right? So detection is used in the identification of friend or foe, right? One of the most secretive electronics in all defense electronics, right? IFF, but that's work out. Okay, so just how do you adapt this to indoors, where your ghost image is a lot, right? In open space, you have ghost image from the, say, sea level or ground reflections or ionosphere reflections, but they're limited. Okay, so if you can use algorithm to figure out what is a ghost and what is a real image. In indoor, there's a lot more of this multipath, difficult to figure it out, right? So reductions of the multi-path is a very important step in locating. Right? Most of the things figured out. It's just that if you have way too many ghosts, right, it makes your system easy to fail. Right? If I can reduce the number of ghosts that you have to do with the reflecting surface, then you get much better ranging. So, but remember that the harmonic, right? There's only one multipath left, right? It's from the reflected harmonic generations to a reflector and coming back. That's the only thing. Every other thing on the fundamental frequency doesn't count anymore. Okay, so that's the things, right? So on this one, phase in the nonlinear transmission line have one more surprising thing. Okay? The phase propagate, I get a smaller phase noise in the second harmonic than the fundamental. Okay? It's actually less than 6 dB. Totally confused me, okay, and I haven't figured it out. Why? Okay. So in theoretically, if you have a phase noise and you convert it to a second harmonic, you at least get 6 dB more phase noise. But what I measure all the time, 3 to 4 dB. I don't know why. Okay, so I try all the experiments and things, theory. I cannot figure out why my phase noise is actually small. Okay, let's just take that. Okay, I preserve the phase. Okay, in these harmonic generations, I didn't know the theory why it's actually even better. Okay, but the phase is actually rather preserved. Okay? I need to work on the worst case so that the phase contains the most ranging information. Okay, so if you look at the conventional ways of getting the ranging, right, from any reflecting wave, it's for sure this is the speed of light, right? You get this is the signal you get, right? But the actual have this wavelengths ambiguity. Okay, so you are limited by the bandwidth of the Q and I, the implementation of the grabbing the phase. Okay, the ratio of that, you are limited by the phase, by the amplitude of wavelength ambiguity. Okay, so how do we resolve that? Okay, so taking that, okay, just doing the simplest things. The first dependence is on what is the signal to noise ratio. Okay, when you have a lot of noise, right? Apparently you cannot resolve the phase as well. Okay, so we need in the simplest equations about a 35 dB signal to noise ratio can give you this range of millimeter range of precisions. Okay, these are first measurement. Okay, first measurement. If I get 0.6 degrees in my phase or 1.8, what are the behavior for the position? Okay, you can use these informations to these. This is trilaterations, right? To pinpoint the exact locations, right? You use different antennas with known positions and trilaterate the positions, and this is something you can do easily. Okay. Then I ask the question, okay, can I do better? Can I do two frequency, right? Or can I do two frequency calculations? Okay, you can dial the in order to avoid the wavelengths ambiguity, your bandwidth is limited, okay, or else you don't know where it is. Okay, it's in multiples of the quarter wavelengths. Okay. So this is the constraint. But if I change the problem, if I poke the things with 4 frequencies, I'm asking that which one is the best possible range. Okay, you work out the math and you find out by the proper selections of the frequency, you can do a lot better. Right? It's called the multi-frequency continuous wave method. Okay. Not invented by me. People have figured it out. Okay. But this really helps. Okay. This really helps. Remember, the enemy I'm fighting with, right, is the phase noise, right, out of this multipath, and the ambiguity of the wavelengths. Okay. So by designing a multi-frequency optimizations, I do better on those 2 aspects. Let me spend a little bit of time on these pretty amazing to me figures. Okay, if you use dual frequency, okay, and use just phase difference of the 2 frequency, this is the phase ranging error with respect to phase error. Okay, phase error bounds. Okay, it's reasonable. It should obey something like this. Okay, obey something like this, right? If you want to get really good precision, you need a really good phase bound, right? But if you allow multiple frequency, giving a relatively large bandwidth, then I can tolerate a lot more phase errors because it's an optimization process, right? So so even I have large phase errors, I can still do good ranging precisions. Okay, so these are one surprising thing. Second, in dual frequency, that if you get the frequency higher, the precision doesn't improve, okay? Even though you have a smaller wavelength, because it's limited. By now you have more ambiguity, right? Yeah, when you have a smaller wavelength. But when you do the optimization, you can continue to improve the precisions by designing the choice of frequency smartly. Okay, so this is if you can push the frequency higher, right? Given a 5 degree, which is not require very precision electronics to do, okay, and I can get a very, very accurate ranging information, okay. And this is fine because I switch the things to optimization. Okay, don't do direct calculations, which always amplify the noise, right? But you use a step of optimizations to improve in the large error bound of phase noise. I can still do better. Okay.
Question?
Yeah.
That was at a 3 meter range.
Yes.
What does the room look like? I mean, how tall? I mean, it's got a ceiling, a floor, walls, and nothing in it?
No, it's all the cabinets.
It's a what?
A metal cabinet.
It's a metal cabinet,
Right.
3 meters long,
Right.
with, you know.
The room is more than 2 meters long, right? So the two things are separated with
Okay.
So are these experimental or are these simulated?
this one, it's simulated. This is experimental.
So the rooms are empty though.
Relatively
With the ceiling
empty.
and floor.
Well, looks like, I
That's what
thought you had a picture I saw.
Yeah, I do. Let me. I will show you the room. Sorry. It's a funny room.
Okay. Yeah, yeah.
Like orbit.
Right.
Okay.
Very nice.
It's not with all these gigantic reflectors and total isolation. I probably can do better in that kind of cold room. Okay? But this is real room. Okay. So the message to you is that if you work with harmonic backscattering, the fundamental advantage for just reading the digital ID is not a lot because you have a fundamental disadvantage of harmonic conversions. And the fundamental advantage is that most of the multi-path doesn't matter. Okay, but for ranging, since most of the issues is at the multi-path thing, which is dramatically reduced. Okay, harmonic has a chance. Okay, that's the fundamental advantage become much more important. Okay? And if you use the optimization instead of using just direct calculations, you can do the next level of precision, which is common in most of the math problems, okay, that do not do direct calculations where error is always amplified and things. Do a optimization problem, right? So you can get a better resolution. We make more measurements and putting all these reflectors and things, and for the ranging errors. Remember, these ranging errors is by tape measures. Okay, so the measurements of the ranging error is probably larger than this. Okay, so it's just that the ranging error caused by the phase noise is smaller than what I can measure. Okay, these are just something that I tell the student you cannot measure 0.06 right with the tape measure. So, but these are from that telling you that under these conditions is actually from the phase noise. Okay, it doesn't dominate the things. You can wave your hand, you can walk around, and things is stable enough. Okay, give you very sub-millimeter precision still. Okay, so okay, let me tell you the conclusion. Actually, 15 minutes time because I jumped over all the whatever data modulations, which is you can get it from anywhere. Okay. So harmonic, the RFID transponders is reduce the self-interference and multi-path. Okay, that's the fundamental advantage. Okay, disadvantage, well, you have the additional harmonic conversion loss. Okay, and I show you the nonlinear transmission line. It has a special property of no spectrum filling, or spilling. Right, you can by setting the Bragg frequency, self-impedance match, right, self-impedance match. And reduction of phase noise, which I don't understand why, okay, up to today, okay, but by measurement it's reduced, okay, and so that is well suited for the ranging purposes, okay, and you can design a nonlinear transmission line to be very high frequency and on the integrated circuit platform, that as I mentioned, you can do PCB, right, 900 megahertz and 1.2 gigahertz on the PCB. Relatively, people have built a lot of this for instrument reasons. Okay, so these are well understood how to do those, and there's actually interesting applications to the ranging. Okay, data modulation we can do very similar to the either putting the modulations on the varactors bias, okay, seeing different nonlinear range, or at different terminations of the transmission line can modulate data that way. And precision locating with harmonic, right? This is the message that I mainly want to focus, right? Actually, harmonic, right, backscatter can do, okay, in indoor ranging with a fundamental advantage. Okay, coupling with the improved algorithms. Okay, this is something that we can do. This, if we have one more bullet, okay, it takes time to explain. Okay, the present budget for doing one range calculations. Okay, there are several concerns. Is the two constraints. Okay, first is the how much time you sample the counting wave. Okay, that's one time. The second is that from this you need post-processing or phase information to do calculations, computing time. Okay, the optimization we have figured out the algorithm as well, but it's ample room to fit the 1 kilohertz, which is something in the title I call it real-time locating systems. Okay, real-time locating system, the present spec. If you can give 1 kilohertz, okay, that means I get your positions 1,000 times in a second. Then you can claim this is RTLS, okay, real-time locating systems. And there's ample room in 1 millisecond. I can fit all this into the. So this is I put a last claim. RTLS actually is doable in this. Okay, it's the precisions of sub-millimeter. Okay, and the time is sub-milliseconds. Okay, I can give you that precision in measurements. How can you do? What can you do with it? I don't know yet. Okay, still try to figure out. Okay, but this is unique capabilities in this harmonic RFID